Alright, hello and welcome to a new video in a course on machine learning. So in a previous video, we discussed the basic introduction to machine learning. We just discussed the linear regression model. And today we're going to be discussing a yet another supervised machine learning algorithm known as the logistic regression algorithm. So consider the problem of classifying an email as spam or not spam, right? So this always happens. This kind of problem, we always encounter it. For example, if you've used Outlook, you always have a spam folder, and it's natural to ask you or to wonder how this process is done. And one way of doing that is one simple way of doing that is like to use a logistic regression model. So what is this about? So in logistic regression, what we do is that we start so this is the simplest logistic regression model that we'll be discussing here. So what we're gonna do is we're gonna start with two predefined categories. And then what we're gonna do is, as usual, we're gonna start with with a data set. Let's call it D. It's gonna be or S usually it's called. So we're gonna start with a set of features and labels, and the labels are gonna be these labels are gonna be either 0 or 1. And the 0 is gonna encode the first predefined category we're thinking of, and the 1 is gonna encode the second predefined category. For example, 0 can encode it's not spam, and 1 can encode that an email is spam, for example. And remember, usually the feature vectors are in R to the D, and D is the number of features we're using to predict the label. And what we're gonna do here is that, we're gonna eventually, what's the purpose? The purpose is we want to start with an input, and we want to output a label, right? What we're gonna do to solve this problem or to predict the label is we're gonna take every feature vector which has D features. What we're gonna do is we're gonna look at, let me just write this notation. We're gonna look at a linear combination of the features. Remember, each xi can be written as xi1 xid. It's a feature vector. We're gonna look at a weighted linear combination of these feature vectors, features inside a feature vector, and we're gonna add a bias term. So by doing so, we're weighting, for example, let's say each xij, it says something about a word that appears in the email, and we want to weight these words, right? In the sense that we want to say that if a particular word appears, then the email looks more suspicious than if another word appears, and so on and so on. So the idea here is that we're gonna weight the features, and we're gonna take a linear combination of these, and then we're gonna add some bias bi. Alright, so up till now, it looks like we're doing something like linear regression, so we're not adding anything new. So this won't be helpful in determining the label which is in 0, 1, because this sum is gonna be just some real number. And it won't be helpful in determining what the label is. So what we need to do instead is that we want to project this real number into the 0, 1 interval, and then we're gonna use that as a probability of the email being spam. So or not spam. So what we're gonna do is we're gonna take this real number and input it to some function that has output in the 0, 1 interval, and then we're gonna use that real number that is between 0 and 1 as a probability of the label being 1 or 0, for example. Okay, so what kind of function will help us do that? Well, we can simply use the well-known sigmoid function. And you may ask, why are we choosing this particular function? Well, there's no one and only choice, but this function is kind of nice to choose because of some properties that we're going to talk about later. But one of the most important properties is that this function is very smooth, right? It's C infinity, and differentiating it is super easy. So we can just differentiate it, and it's differentiable everywhere, and we have the property that it has a range that is 0, 1. Okay, so let's put things in a compact form and restate what we just said. Alright, so we want a way of telling the probability of the label being 1 given an input x. So given an input, a feature vector x, we want to give a label, either 0 or 1. So what we're gonna do is, we're gonna find the probability that y is 1, that the label is 1 given an input x. And if this probability is bigger than half, we're gonna give the label 1, and if it's less than half, we're gonna give the label 0. And the reason we want to do this is because if the probability when y is 1 is bigger than half, then automatically the probability of y is 0 is less than half. In other words, the probability of y is 0 is going to be less than the probability of y equals 1, and hence we want to assign the label that has the highest probability. So what we're gonna do is we're gonna take this real number that we obtained, that's gonna be a number in 0, 1. We're gonna take that real number and we're gonna use it as the probability that the label is 1. Okay, so this is the big picture. However, as it is always the case in supervised machine learning algorithms, when we introduce a weight, like when we introduce this weight, we need to find the weight, right? So we need to find the weight vector that will help us predict the label for unseen data. So we want to use seen data to find the label, the weight omega, and from that, after we find omega, predicting a new label will be super easy, right? I can simply predict what the label is by just using this as the probability of the label being 1. So notice here I just omitted the bias. You can add it, that is fine, but just to simplify the discussion here, I omitted the bias from the discussion. Alright, so we have this model, we have this way of solving the problem, of solving any binary classification problem, and by that I mean the label is in 0, 1, right? And you wanna, for a given input feature vector, you wanna choose a label. This is a binary classification problem. We have this setup, and what is left to be done is that we want to find a way of finding the weight vector given an initial training data set. Alright, so let's see how we can do that. Well, if you recall when we discussed linear regression, we had this idea to find the weight vector, we had to introduce a loss function, right? So we need to see what kind of loss function we can introduce here, and to introduce a loss function for this particular model, what we need to do is we need to use a principle that is widely used in machine learning. So we're gonna discuss this principle at a more deeper level and more rigorously in coming videos, but for the purpose of this video, let us just get an application of it that's gonna illustrate how it works. For logistic regression, the likelihood is gonna be the Bernoulli likelihood. So recall what we mentioned is that we're gonna take sigma of z to be the probability of y equals 1 given x, and to be more precise, we mentioned that sigma of omega transpose x is going to be this thing, and to get the optimal model, what we need to do is we need to maximize something called the likelihood. And the likelihood is going to be just simply the probability of y being 1 to the power of y. So remember, y here is in 0, 1, right? So when y is 1, I want the probability of y equals 1 to appear. And when y is 0, I want the probability of y equals 0 to appear. So we're gonna use this Bernoulli likelihood. Again, there's a rigorous reason why we're doing this that we're gonna postpone for now, but you can bear with me in this video and take it for granted that there is something called a likelihood that is that we can introduce, and for this particular case, it's gonna be the Bernoulli likelihood, and we want to maximize this. Now, maximizing this will give us the optimal model. Now, we observe that maximizing this likelihood is equivalent to minimizing minus log of that. So if we look at minus log of that function, since the log is an increasing function, then like maximizing the L function, the likelihood function, is equivalent to minimizing minus log of that function. And minimizing minus log of that function is like a typical thing that we'll be doing in this course, and it's called the log likelihood. So when we take a log, basic properties of the log gives us this, and we have this minus over here, and this is going to be our loss function. So this is going to be taken to be our loss function. So I could have just told you that we're going to choose this to be our loss function and we want to minimize it, and we're going to get the optimal model, which is okay, but I figured that I should say a word about the likelihood because it's going to appear soon. In other words, the choice of the loss function, there's a reason for this choice of the loss function, which we're going to see in coming videos. So this is the loss function that we're going to minimize, and if we minimize this, we're going to get the optimal, we're going to get the optimal model. And remember here, the right hand side depends on omega because every z is omega transpose x. Okay. So when we say we want to minimize this function, what do we mean exactly? Well, we mean we want to choose the optimal omega that makes this the smallest, right? So this is our goal. So how do we do this? Well, we've now seen a way of doing this that's not hard. We're starting with a data set, and the yi's are labels in 0, 1. We figured that this is the right loss function to minimize, and we want to minimize with respect to omega, and once we minimize this function, once we find the omega that makes this function the smallest, we're gonna call this the omega hat, and by omega hat we mean the optimal omega that makes this the smallest. Alright, this omega can be derived in several ways, one of which is gradient descent. And if you haven't heard of it, don't worry much about it because we're gonna talk about it in coming videos. But of course, another way of finding this optimal omega is to zero out the gradient. So you may as well consider finding the gradient and zeroing it out. I'd like to note here that there's a nice property of the sigmoid function, which is that its derivative is equal to itself times 1 minus itself. So this is kind of a nice form of the derivative that you can use so easily. But again, I prefer gradient descent for the purpose of this function. And we're gonna discuss in next videos how this gradient descent thing works. But let's take it for granted for now that one can either like minimize this using the gradient zeroing method that we discussed for linear regression, or we can simply just use the gradient descent algorithm, which we're gonna touch upon in the coming videos. So just to wrap things up here, we took this sigmoid function to project the linear part taken from like a linear combination of the features to the 0, 1, because the sigmoid function has this range. It has the range 0, 1. And what we did is that we said that we're gonna find the omega, the optimal weight function, the optimal weight vector, excuse me, by minimizing some loss function. And once we find that optimal weight vector, what we're gonna do is, like given a new feature vector x, we're gonna just take that and dot product it with the optimal omega, then compose with the sigmoid function to get a probability or to get a real number between 0 and 1, which we're gonna regard as the probability of the label being 1. So we're gonna use this as the probability of the label being 1, and we're gonna predict the label of x to be 1 if p hat is bigger than or equal to 0.5 and 0 otherwise. And with this, we have a light introduction into logistic regression. We're gonna expand on this in the coming videos, where we'll discuss like what happens if we have more than 2 labels, and then the discussion of softmax classifier will come into the picture. And we're gonna see also that this logistic regression is just like, it's a particular instance of what's so-called neural networks. Specifically, we're working here with one neuron, and we're gonna see how this is just a special case of this world of neural networks as we go in the course. So stay tuned for that.